Hi, welcome to this video in which we will talk a little bit about how to perform a group level cluster based permutation in MATLAB, and we are going to use our library or package Lively Vectors, and we are going to also discuss the main concept of cluster based permutation and how to perform it. So we are just gonna try to understand today what is cluster based permutation and why we need it. So the result of a cluster based permutation will look something like that. If you have two conditions, in this case I had two conditions, one experimental and one adaptation, and you have this solid line representing the mean coming from different participants, and here you could have any measure, and you need to basically compare the two conditions, whether the effect is significant during some time periods and it is not really significant during some other durations. So we are going to see how we can apply cluster based permutation and extract our significant clusters and get the exact p-values and stats values for that. So let's start from the very beginning. Why do we need such thing? So we can imagine that we have started collecting some samples, and we have a sample from every participant, and our sample is looking like this. So it's something across time. So this could be actually the ERP. So this could be the average of a lot of samples in our participant for a specific condition, and we have collected data from another participant and a third participant, and so on. We have collected data from a lot of participants, and we looked at this and we inspected this, and we felt like, okay, we might have something interesting around this time region, right? So we wanted to check if this is true. So what we did, we collected data from another condition. It's a control condition, so it's almost flat. It doesn't have the same effect that we are looking for. So now we are left wondering how we are going to compare these two conditions and end up with a cluster or a kind of statistical analysis that would reveal this difference. Okay, so we have this from condition 1 and condition 2, as we said, and we can just represent them in a nicer way. So here I've just separated them like that, and here we have condition 1 and here we have condition 2. So now we need to think about every time point from our ERP and every condition. So we basically think about the first time point, and then we extract the value from this time point for the first condition, and we do the exact same thing for the second condition, such that we will have a direct comparison basically for the first time point between condition 1 and condition 2. Okay, so we repeat this for all time points, and then we're going to take the difference between the signals. So repeat this for the second time point, third time point, and so on. So we can basically think of this as just we are aligning the signals, taking the difference, point-wise difference, such that we end up with something like that. So we just end up with the difference between the two conditions. So by the way, with this one, I'm just talking about the group level cluster-based permutation. We are going to discuss this the same thing if we are talking about participant level. The difference would be that trials or samples are not paired, but the concept itself is generalizable to different cases. So here we are looking at the difference between condition 1 and condition 2, and I am here interested in the positive effect. So basically I'm assuming that there is a positive effect in condition 1, and that's why I'm subtracting condition 2 from it. So here we are looking at the difference, and what we are gonna do right now, we are gonna take our first vector, our first time point, and we are gonna move on it. So we are gonna basically slide over all of the time points that we have, and then we are going to calculate our favorite statistics. So basically with this one you have a vector, and you can compare this vector to 0 because that's the difference. So you are now free to compare this to 0, and you can calculate the t statistic for this time point and do the same thing for all time points, or you can do a Wilcoxon signed rank test or something else that is not non-parametric if you would like to. It all depends on if your data is normally distributed or not, if you have any assumptions about your data. So, and then you can basically, instead of looking at that difference, you replace it with the t stat, for instance, such that you will have a curve representing your statistical values like that. So as you see, we are taking the curves, taking the difference, and then applying our statistical analysis, and then you have a stat value like so, and then you can threshold this and see where you have a significant difference, where this difference is significantly different from 0. So we can analyze this and see that our ERP is different from 0 during this duration. And we can also think about another example. So in this example, it's very clear that there is a difference around this point. So here I would like to highlight the main difference between cluster-based permutation and doing something else like Benfroni correction and get your clusters. So basically, let's say in real with real data you have something like that. So your stat values are looking like this, and you have thresholded your data, and you have looked at a lot of significant effects like that. Okay, so the issue with that, you have a lot of clusters, right? So with real data you wouldn't get this as something significant. You don't like this to be significant because it's a very small cluster, but of course this is going to be according to the code, it's not by just visual inspection. So the thing is, now if you are applying something like Benfroni correction, the difference would be that it will depend on the number of points that you have. So what this correction will do will basically, instead of having your threshold at this point, it will look at how many comparisons you have. So what is the number of samples that you have in your data, and then it will raise your threshold by this amount. So it will be very difficult for an effect to be significant by doing Benfroni correction. And not only that, so the main concept behind doing cluster-based permutation and not doing just Benfroni correction like that is this, that we are depending on the number of points if we are doing Benfroni correction. So if we extend our signals to be like double the length of this signal, then this threshold will be in a totally different position, and these clusters will not survive. And in the meantime, the issue I have just mentioned is actually something in cluster permutation as well, but the main difference here is that in cluster-based permutation the whole cluster will survive as a whole, or it wouldn't survive. So the whole cluster will survive or not, because we are doing permutations and we are trying to see if the whole cluster will survive at once or not. But in the meantime, with Benfroni correction, if you extend the signal, you are raising the threshold such that your significant cluster will be shrinking. So it will be a smaller cluster because you have raised the threshold like that. But with cluster-based permutation, we are looking at the connected points that are significant for this particular threshold. We are not raising the threshold, but we are taking this value of the t statistic, and then we are comparing this to shuffled data, a lot of permutations. So we take our stat value, and we threshold this value with the t stat, and then that is significant. Of course, it could be 0.05, which may correspond to 1.96, or it's all up to what you are testing and the significance level that you are testing. And then we say that this is our observed stat. So we can basically take the maximum of this region, or we take the whole, like the summation of this area. So we basically sum all the t stat values inside of this significant part here, and we say that this is our observed statistic. Okay, and what we do next is interesting. We start our permutations, we start our like shuffling. So what happens next is that let's look at our conditions, and what we will do, we will start shuffling our data. So we basically assign the signal to a different condition. It will be condition 2, and this one as well. So we can just shuffle our ERPs between participants, or not between participants, it's at the same participant, but between conditions. So what we can do is something like that, where we can swap our data between conditions. So basically we can do something like this. So we have then flipped the conditions, we are shuffling our data, and then we can just I'm just recoloring them according to the condition, and that would be our first permutation result. So we are basically shuffling the conditions for the same participant, and then we can repeat what we are doing. So basically we go at every time point, get the difference, and then calculate our t-stat, and then we can, for this first permutation, threshold our t-stat, and then take the summation inside of this area, which will be our first t-stat from the first permutation, and then we repeat this thing. So we shuffle our data, we get new data, completely different shuffling, or the same shuffling, it's random. Okay, so we shuffle this many times, get a second permutation, we threshold this and see if there are any significant ports. We just sum this significant regions here, there are none, and so on. So we do this for like 10,000 times or something like that, up until the point we can get a distribution of values for all the shuffled data. So our distribution will look like this. So we basically look at the frequency on the y-axis and look at the stat values on the x-axis. So it will look something similar to that. So we will have a lot of permutations, basically getting this stat value. That's why the frequency is so high. And if you go to the very extreme stat values, very high t-statistic values, you wouldn't see a lot of permutations giving you this value. And now we are left with the very important question. We had an observed stat, we had an observed t-statistic, right? We take this value, which was the summation of our significant cluster, the summation of the t stat value, and then we compare it to this distribution. We see where it falls in this distribution, and we count how many permutations exceed this observed value. Okay, and this will give us our p-value for the test. Okay, so when we see how many permutations exceed our observed t-stat, is it like less than 5%, then it's a threshold, it's an alpha of 0.05, because we have 5% of our permuted data exceeding this value. Okay, and when we have less than 5% of permuted values exceeding this value, this observed value, we say that our cluster is significant. Okay, and of course this depends on the kind of test that you are doing, whether it's one-tailed or two-tailed, but the concept itself is is the same, that you are looking at the permuted and seeing how many of them are higher or maybe lower than your observed stat value, and then you are comparing this to your threshold 0.01 or 0.05 in this case. Okay, and we can even extend this to look at 2D data. So that's exactly my objective with this tutorial, to say that this can be extended for any dimensions. It is not exclusive for just 1D data or ERP analysis. It can be extended for time frequency analysis as well. And what we were doing here, we were looking at time points that are contiguous and are neighbors to each other in time, right? So in this one, we were looking at some time points that were next to each other, and all of them are exceeding our threshold. So right now, instead of looking at this as 1D, as just this curve, we are looking at the same thing but now 2D. So let's apply the very same concept that we discussed. Okay, so let's look at this. We have a condition 1, and then a second condition, and then for each one of them we have a time frequency analysis. So what we do next is the same. We take the difference between the two, element-wise difference between the two, such that we will have a 2D differences, a difference for every participant between conditions. Okay, and then we look at every point of this. So every point across all participants will make a vector, and then you take this vector of the differences and you compare it to 0. Okay, and you do this, you repeat this for all of the 2D figure. So we can imagine that this arrow is just moving on all of these figures, and every time we see a vector, and we are comparing this vector to 0. Okay, such that when we end doing this procedure, we will have a 2D figure representing the stat value at every point. Okay, and what we do next is exactly the same. We see where our stat value is significant, and we say that this is a cluster. So our stat value may be significant, let's say in this region. Okay, in this region. So we will say that this is our cluster, and then we will sum all the stat values inside of this cluster and say that this is our observed. Okay, this is our observed stat, and then we are going to do the permutations. We are going to shuffle the data between conditions for the same participant, and then we are going to have a lot of shuffled or permuted data, and for each one of them we take the summation of the clusters that will be significant, and then we create a distribution of shuffled data, and then we see if this observed value is significant or not. So it's exactly the same procedure. Okay, so then what will happen if you have 3D data? It's exactly the same thing. So the main concept is that you are taking the difference, you are then looking at the stat values at every point in this high dimensional space, it doesn't matter. Okay, and then you are looking at the neighboring nodes or the neighboring points, and then you are summing the stat values inside of these contiguous significant points. Okay, and then you have a difference, you have a stat value at every point, and then you look at the significant parts. So the significant region would now be 3D, so it's almost like a sphere. Let's imagine that this is a sphere and significant, and then you do the same thing. You take the observed stat, you do permutations, you have a distribution, and then you ask the question if this is significant or not. Okay, and you can even extend it to 4D or something like this, and it all depends on your data. So why I'm doing this, I'm just showing you that this is a general concept that can be extended to any dimensions, and it's very important to think about this in a very generalized way, because with this you can even extend it to a topography, basically, where instead of looking at the contiguous significant time points, you are looking at significant electrodes that are next to each other. The concept is the same. Now, instead of looking at the effect temporally, where the contiguous time points are actually time points, they are electrodes. So you are looking at the effect spatially. You are looking at the effect in a space instead of being in time. Okay, so this is extendable to any kind of data that you have. The concept is the same. Okay, so next we will be looking at how to do this in MATLAB, and in the next part we will go over lively vectors, and we will see how we can do this with lively vectors, and we also will see how to do this with field trip and MVPA light, and all of them are doing this kind of stats.